All right, let's talk about something really cool. What if you could tell a real object from just a trick of the light, simply by looking at its shadow? I mean, really know it's real. Well, that's pretty much the core question behind one of the greatest unsolved mysteries in mathematics. And yeah, it's a big deal. So big there's $1 million prize attached to it. We're talking about the Hodge Conjecture.
So at its heart, the whole thing boils down to a surprisingly simple question. Imagine you see a shadow on a wall. How could you prove it's being cast by a real, solid object and not just, some weird trick of the light? That very simple idea. That's the key. That's what we need to unlock the Hodge Conjecture.
Okay, let's make this a bit more concrete. Think about a snowflake. I mean, that stunning six-pointed symmetry we all know. That's not just a coincidence, right? It's not an accident. It's a direct reflection. It's basically a shadow of the hidden geometry of how water molecules lock into place on a deep, deep level. That pattern reveals a deeper reality. And the Hodge Conjecture basically says, hey, what if that same principle applies in the totally abstract world of mathematics?
All right, so first up, a shadow of geometry. We're going to break down the tools mathematicians use to tell the real shadows from the fakes.
So in math, there are kind of two main ways we look at shapes. On one hand, you've got topology. This is all about the most essential properties of a shape. It's topological shadow, if you will. Think about it like this. A donut will always have one hole, no matter how much you stretch it or squish it. That's topology. But then, on the other hand, there's geometry. That's the actual rigid object with its precise angles and curves. The whole mystery is connecting the two. When does the shadow actually prove the object is real?
Okay, to really get a grip on this, we need to meet the key players, because this isn't just about shadows and objects. It's more like a story with three main characters from the math world.
First up, you've got topology, which gives us those flexible shadows. Then there's geometry, which gives us the solid, rigid, real objects. And the all-important bridge that connects them? That's algebra. Algebra is the language, the set of equations that can describe these geometric objects with perfect pinpoint precision. It's what turns shapes into symbols we can actually work with.
So what kind of shadow are we actually looking for here? Well, it's not just any old shadow. We're on the hunt for a very special one called a Hodge class. The best way to think about it is it's a shadow that has this specific kind of mathematical symmetry. Its structure is so neat, so orderly, that it just looks like it has to come from a real, well-defined object. It has all the fingerprints of something genuine.
And that real object, what is it? It's called an algebraic cycle. This is the actual tangible thing casting that special shadow. It could be a point on a line, a curve on a surface, really any shape you can describe perfectly with algebraic equations. So let's get this straight. The shadow is the Hodge class, and the object is the algebraic cycle. The million-dollar question is, are they always linked?
Okay, so we've met the players, the stage is set. Now for the conjecture's big idea. What's the grand, elegant claim that this whole thing actually makes?
And here it is, the punchline. The Hodge Conjecture states that for certain types of mathematical spaces, this connection is absolutely perfect. Every single one of those special shadows, those Hodge classes, is, in fact, being cast by a real geometric object, an algebraic cycle. No exception.
And this quote just nails it perfectly. If it looks algebraic, something algebraic is really there. No fake symmetries allowed. I mean, what a profound statement, right? It's saying that in this special mathematical world, there are just no coincidences, no flukes. If a shadow looks like it was cast by a real algebraic object, then it was. Period. The system is perfectly logical, no tricks.
Okay, but there is a crucial catch here, a really big one. This perfect alignment, it doesn't work for just any old shape. It only seems to hold true for a very special class of mathematical spaces called projective varieties. So what makes them so special? Well, to put it simply, these are spaces that have a really rigid, almost grid-like structure that is itself defined by algebra. It's like this rigid algebraic backbone is what forces the shadows and the objects to line up so perfectly. In fact, in more floppy mathematical spaces, we actually know the conjecture is false, which is just fascinating.
Look, I know this is all pretty abstract, so let's bring it back down to earth. Let's look at a few concrete examples where we can actually see this principle in action.
The bedrock for this entire idea is a proven theorem. It's called the Lefschetz 1-1 theorem. And what it does, essentially, is it proves the Hodge conjecture for the absolute simplest case you can imagine, for the lowest dimension shadows. And for these, we know for a fact it's true. Every shadow that looks algebraic really is.
So naturally, mathematicians are trying to build on that foundation. You can see the general path a proof might take. You start with that solid, proven base case, and then you use all this powerful algebraic machinery to try and build up from there, step by step. But sometimes the most beautiful evidence doesn't come from a grand general theory. Sometimes it comes from one stunningly specific example.
27. Just the number 27. What on earth could this number possibly have to do with any of this?
Well, get this. It turns out there's this classic, famous result in geometry that says any smooth cubic surface, that's a surface defined by a third-degree equation, contains exactly 27 straight lines, always. And here's the astonishing part. Those 27 real, actual geometric lines perfectly account for all of the special topological shadows, all the Hodge classes on that surface. The geometry and the topology they match up exactly. It is a perfect, beautiful, mind-blowing example of the conjecture in action.
So, okay, finding 27 lines on a surface is incredibly cool, but why does this matter so much? Why is proving this conjecture worth $1 million prize? What are the truly profound implications here?
Here's the big picture, the grand takeaway. The Hodge conjecture suggests that there's a deep, hidden unity in the very structure of mathematics. It's telling us that these two enormous, powerful fields, topology, the study of abstract shapes, and algebraic geometry, the study of equations, are actually in a very fundamental way speaking the same language. It's like discovering two ancient civilizations use the same alphabet. They are perfectly aligned.
And here's another really powerful way to think about it. This one's kind of borrowed from physics. Imagine a Hodge class is like a state of zero energy. It's perfectly balanced, totally stable, and symmetrical. What the conjecture then claims is that the only way to achieve that state of perfect balance is by building it out of the most fundamental pieces you have, the real, solid algebraic objects. Nothing else will do.
And that quote, "Geometry recognizes its own," just brilliantly illustrates the core philosophical idea here. It's as if geometry has this built-in way of recognizing its own reflection. When it sees a shadow out there that has all the right characteristics, it just claims it, says, "Yep, that's one of mine." It's not a coincidence, it's a fundamental property of how the mathematical universe is put together. And so, in the end, the Hodge conjecture leaves us with this really tantalizing question. It points to this deep symmetry, this hidden harmony between two completely different mathematical worlds. And it just makes you wonder, what other secret alignments are out there, governing our universe, just waiting for us to find the right way to look at them?